Today we're going to review some very basic modeling concepts, and the objective is um, to talk a little bit about the bond graph technology as well as the block diagram. How do we actually go and write differential equations on systems from scratch, and how do we actually initiate those models? So that's the topic of today's lecture. So we're going to get started here, and we're going to call it basic modeling concepts. Uh-huh. So here we have a situation where you have a different systems in different energy domains. So it is possible to take some of these examples and just make simple models that actually represent these systems. What is important is that we are recognizing here the way we assign variables, or or you would say what variables we consider on systems that are important. In this case, you see the force and the velocity, of course, are the variables of choice on the mechanical side. The voltage and the current are on the electrical side, and you have torque and angular velocity on the rotational dynamic side, and pressure and volume flow rate for hydraulic systems. Okay, the idea really is to be able to do models and learn control systems of devices that are not strictly mechanical systems. You know, you have to have you can do electrical systems as well. So I think what I think would be helpful is if we take a couple of these systems and develop it, you know, completely. So I think what I'm going to do is I'll take a mechanical system and also an electrical system. In the variables that we just stated over here, you know, those force and velocity, voltage and current, and so on, you can always define power between the elements that transmit to, you know, between systems and components, these two kind of variables. And we're going to call them efforts, and the other ones we're going to call them flows, just so that we can generalize the way we do the models and make it easier to model things in different energy domains. So we're going to use these variables for mechanical systems, this two for electrical, this two for rotation, and this two for hydraulic systems. If you look at the units in here, the physical systems, you have effort and flow, and the units in their energy domain. And so we're going to use four variables: effort, flow, the displacement, and the momentum. And each one of these, depending on which energy domain you are, has different units. However, when we talk about effort, it can be any of these. When we talk about flows, it could be any of these. Displacement, any of these, and momentum, any of these. So that means that by using these four variables, we can actually generalize the concept across energy domains. That means that we could create models of systems that have hydromechanical components, electrohydraulic components, and electronics and mechanical systems. This is the the way we do it in an elementary way. You have the battery, for example, the starting motor, and the Bendix. This is how you start your car. Um, if we put the words, like you see on the red forms in here, those words would indicate the element that we're talking about. And how does the battery communicates with the motor? It communicates through those two power variables, one called voltage, the other one called current. And if you have this for a mechanical system, it would be in the torque and the angular velocity. So that is the so-called bond graphs. Bond graphs, I could call them also union graph or junction graphs or assembly graphs. Um, so if you look in here, the words that represent parts of a system and their connection, you get a connection graph as well. And their connections, you can see that you can model an entire vehicle using this concept. Like you have the engine here, and you have the clutch over here, you have the gearbox in here, the drivetrain, and the differential and the two wheels on the back. It turns out that to be able to implement this idea, each one of these elements have a specific function on the system, right? Like the gearbox and the clutch are sort of like um, in one case it connects and disconnects the system. In the other case, it switches the gears and tells us whether the car is going to go faster or slower, whether you're going to have more torque or less torque. So if we can recognize the type of elements that each one of these represent, then we can actually make the model of this. Now there is an important concept that we need to go over, and that's the concept of causality, and that is the interaction between element A to element B. Um, in this particular case on the left-hand side, A acts on B through this variable E. B responds to A with the variable F. So if I apply a force to a body, the body acquires a velocity, right? So the cause is the force. You may see the consequence or the effect is the velocity. Okay? The way we represent that in the symbols that we're proposing is that you see in the top you have this block diagram that is actually self-evident. Say A applies E to B, B responds with F. This one says B applies E to A responds with F to B. We use this notation, a line and a crossbar. What does that mean? It means that the crossbar is going to indicate to us the way the effort is going. Like in this case, A pushes on B is as if you hold A by the horizontal line and push it towards B as if it would be a piston, then it's obvious that A is applying some force on B and B is responding with a velocity. The force is that one, the red line, and the response to velocity is this green line. If you have this situation, you have the reverse. B pushes on A and A responds with the velocity. And that's what that on the right hand side. So this is perhaps the only part that is really new for understanding the difference between these two methods. But in reality, the representation in the end, whether you do it one way or the other, the results should be the same. You know? So in order to do this, we have to have some basic elements, two sources, this SE and SF, two connections, either a common effort junction like a 0 or a common flow junction like a 1, and 5 other elements. And it's very, it's amazing that with 9 elements, the ones that are laid out on the board, that you can actually do this. Okay, you can actually do this with 9 elements. You can model just about anything under the sun. So let's do a little by little here. So I am gonna put a couple of examples. I mean, to illustrate both of these techniques. So let's exercise the idea of writing the differential equations and then doing the simulation in Simulink both ways. Okay, so let's just, I am gonna go on to my OneNote and use the system that I have in here. You see, the system that I have in here is a force applied, then we have this mass, then there's a spring, and then there is a damper, you see. So every time I move to the right and I apply this force, these two are going to oppose, right? So the way it works is that we need to have, like, what did I call it, collection graph or junction graph or bond graph, a way that represents this connection. Okay, we represent the source of effort for the forcing here, and this one junction is telling that in this system the velocity x dot is common to the forces, to all the other elements. So, but in here between this and the wall, we have some spring and we have this damper also. Our reference point is a velocity with velocity 0, which represented over here. So this is the wall, and the difference between these two are these two elements. So maybe what I should do is, this is the end result as I would like to use to do the simulation. But I think it might be a good idea to repeat this. How do I actually cut this graph? So I am going to go in here, and I think this is the eraser. I think goes like this, yeah. Very good. So let's start now. And here I am going to take some steps that would allow me to to do this model. So first of all, I need to draw, and I need to be able to write on this with use this pen. I am going to use to represent first the junction that represents the velocity. I also going to use another one to represent the velocity of the wall, which would be equal to 0. Yeah, this is how we start. So I think it's important for you to notice which way we, the steps that we take and in which order we do them to do this model. So what I was saying, it starts with the velocities, then goes to the elements in here. So let's just change our view in here to full screen, full page. That way we have more space. So in here you're going to have a let's say a source of effort in here. This is going to be the force F. I put those two little dots to indicate whatever is next to it is the value of that element. So in here I'll say, okay, we have the basic structure, but in here we have to have the connection in here. The I element is the mass in here with value m in here, and I would like to use a different color for the connection. Let me see. Use this one. So we connect the force with the mass, and then see, you connect the force. I mean, yeah, you apply the force on the mass is what I was trying to say. So this is the way we represent the mass. We represent this one in here, this, and then we represent also the mass. That's what you see now here. Okay, so one thing that we're forgetting here is that the source of flow in this case with velocity of the wall equals to 0 is attached here also. Okay, but it is very obvious that from what you see, you have represented the mass, the external forces, and of course the reactions on the CNO. But you see, in this case, in here, let's see if we can maybe use this tool. No. In this case, you have the spring and you have the damper, but those two are in between this, the mass, and the other one. So you represent this, the difference in velocities between this and this point. Okay, so and here we're gonna go and say we're gonna use the zero junction to make the difference between x dot and b, and that difference is going to be a one junction that we represented as x dot minus velocity of the wall, and that difference is seen by the C element, which is there, and also by the R element, which is here. And that's the end of this. We have, in fact, created a bond graph model that can actually be used in Simulink. This is how we represent the system. So now let's try to do the simulation with this bond graph model, and we'll see. Okay, I am going to keep this in a small way. Yeah, here we go. And so we're going to go and run this. Where is the features? Okay, so now we're going to say new, and in fact what we're going to do is we're going to transfer the example that I just did into here. See here, let me just move up a little bit, move this one up and the other one have to be down. There we go. We have plenty of space in there. So let's just go ahead and do this this drawing. As soon as I find the mouse would be nice. What the hell? Okay, there we go. There we go. There we go. Okay. So we go and put the SC over here, and then the one like this, and then we join these two, because now we are just translating something that we already created. Yeah. And then you have the 0 here. Okay. And then we have a 1 over here. And then a C and an R. And then we have the R element. And the SE. SF, excuse me. No, 1. And then the SF, which is over here. And then of course we need a connection between this and this. Undo. Need to correct it a little bit, and then okay, let's move it. Uh, mm, there is something funny about this here. So I would like to see if we can move it a little bit, but not having much luck with it. We're gonna this there's some editing features in here. Like for editing, we're gonna say move segment means move an entire assembly. You know, if you move it from here to here, this is what I was trying to say. See, this is a bit obscure. The reason is that I think is too close. So right. So now what we do is we say interface to MATLAB. Oh, before I do that, what I want you to do is to recognize the elements that are on the right hand side. Mm-hmm. Excuse me, there's ones here on the left hand side, with what we have on the right. All right, we have represented it in an easy way. Right there. Okay. So what I'm trying to tell you is forces over here. Then you have mass over here. The C and the R element, the spring and the damper are here, and the wall is here. So we need to put the values on this. The way this works is say like interface to MATLAB, please, and then we wait a little bit. CamG, which is the software that I was using, and MATLAB are negotiating right now, okay, some interface between the two programs, because what CamG is going to do is send the information of this model directly into MATLAB. In MATLAB, we need to do just the stating what the parameters are, and this should be able to do what we need to do. So we'll wait a little until MATLAB decides to come up, and then what's important to understand here is that bond graph model I was entered into CamG is going to be transformed into an M file. But you see, whether you do it from the bond graph or you do it from writing the equations by hand, you still need to create this script called M file. What's happening here is, and with the handshake between these two programs, what's happening is that CamG knows exactly what MATLAB wants and is going to deliver it such a way that if the system is linear, all you have to do is to put the initial conditions, the physical parameters, and the outputs, and then you should be able to do a simulation. So now a MATLAB came up, and what we have is what we have is a set of files, a set of M files that have the description of the model, and all those were computer generated in such a way that you don't have to be writing these equations by hand. So there are 4 files in here. Right now we need to worry about CamG, CamG EQU, but mainly a CamG mod file See what it says in the initial conditions. These are 0. Okay. Then you have the values of this. Maybe let's do this as a 2. Okay. C is 1 over the stiffness here. So it's 1 over k, so like 1 over 40 or so. And then you have their element maybe 3. So I'm putting some reasonable numbers so that I can get a response. SE is, let's say this is 1, or let's just say, call it 10. Yeah. This was the velocity of the wall. The initial time here, 0. And then you have the final time, 5 seconds. Okay. Okay. So right now what we need to do is, once we put the physical parameters, we run it from here. And we should be able to get some response. See, in fact, it does. So in here we have the input as a step input, and this would be the response. And we could plot many of the variables in there. But this is how you run a simulation as a basic set of steps to, in an elementary way. I have explained how you could start with this model, generate a model, and do the simulation.